Okay, good evening. It's April 27, 2023. This is Professor David J. DelosReyes. Okay, my topic for tonight will be the worst case scenario under circuit analysis using Laplace transform. That is the series RLC-AC circuit. The solution should be by using Laplace transform. Okay, I will check my calendar. Okay, let's proceed. The boring times is almost done. Okay, so this will be the last part of the so-called circuit analysis by using Laplace transform. Okay, the topic for tonight will be advanced math, lesson number 34. The circuit is a series RLC-AC circuit. The solution should be by using Laplace transform. Meaning, if we are given a figure that is, the connected components are actually a resistance, inductance, and capacitance, the connection is series, energized by an alternating current source, okay? The requirement of the problem is what will be current as a function of time by using the solution should be by using Laplace transform. We are done with the solution of this circuit here by using the classical solution, that is differential equation. Okay, I will give you the total final current before I will start with the solution by using Laplace transform. Under the so-called classical solution, the total current as a function of time for an RLC series alternating current circuit, it got two components, that is actually complementary plus the particular. For the complementary part, we got three cases. That's why there are three equations over here. This is for case number 1, this is for case number 2, this is for case number 3 for the complementary solution. And for the particular solution, it is just simply one equation, that is E sub m over the impedance sine of the quantity omega t plus angle p plus or minus angle theta. This is actually the total current as a function of time from the previous solution, classical solution, that is differential equation. So for tonight, we will derive this equation by using Laplace transform. Okay, let's proceed. To start the solution by using or for finding current as a function of time using Laplace transform, we will start with the so-called summation of voltages, and they should be equal to 0. We close the switch, then we take the summation of the voltages, and they should be equal to 0. That is actually Kirchhoff's law. Okay? That is plus E minus B sub R minus B sub L minus B sub C, and the sum should be equal to 0. This is a voltage rise, a voltage drop, a voltage drop, a voltage drop. So the summation of a voltage rise and a voltage drop should be equal to 0. Okay, substituting values. The equation of the applied alternating current voltage is actually E sub m sine of the quantity omega t plus angle p. It is a sinusoidal AC voltage. Okay? This value here refers to E sub m, meaning E maximum. And the equation of this is E sub m sine of the quantity omega t plus angle p. The abscissa is time, and the ordinate is voltage. Right? It's a sinusoidal. So this E sub m here refers to the maximum voltage. Okay? So substituting value E sub m sine of the quantity omega t plus angle p, that is E, the applied AC voltage, and they should be equal now to the product IR. These three here are all negatives. I place it on the right, so it will become IR, the voltage drop across the resistance. And the voltage drop across the inductance is actually L di dt. And the voltage drop across the capacitance is actually 1 over C, the integral of I dt. The integral of I dt is actually the charge on the capacitor. But for a capacitor, the current is changing. That's why we got an integral of I dt over here. Okay? So the resulting equation, okay, I will try to erase this one. The resulting integral differential equation now will be this. This is where we will derive capital letter I as a function of S. Because the Laplace transform solution is actually from function of t to a function of S. So to derive this capital letter I as a function of S, we must have to know this one by taking the summation of voltage equal to 0. Okay? So the next step is actually take the Laplace transform of both sides. Okay? For the left-hand side, E sub m is constant, so this should be E sub m. And the Laplace transform of sine of quantity omega t plus angle p, go back to your transformation formulas. It is actually S sine of angle p plus omega cosine of angle p all over S square plus omega square. That's the Laplace transform equivalent of the quantity sine of the quantity omega t plus angle p. We derived that one. It is one of the Laplace transformation formulas. Equal to, on the right hand side, I is a variable, right? And R is constant, the resistance. So if we take the Laplace transform of the product IR, it will be R. And the Laplace transform of the small letter I will be capital letter I as a function of S. And for di dt, we are given a transformation formula for the Laplace transform of a derivative with respect to time. That is, if we try to take the derivative of L di dt, it should be L, open bracket, S, capital letter I as a function of S. Plus some initial condition, but that initial condition is actually plus 0. So I didn't place 0 anymore over here. Okay? So meaning the Laplace transform of L di dt will be L times S, okay, capital letter I as a function of S, plus 1 over C. The Laplace transform of any integral thing is actually 1 over S times I as a function of S. Okay? Originally, this was capital letter F. But for the meantime, the variable we are talking is actually current. So instead of capital letter F, it should be capital letter I as a function of S, close bracket. So simplifying this one, all the terms on the right got an I as a function of S, right? So we factor out times open bracket R plus LS plus 1 over CS, close bracket. That's the simplification of the right hand side, but we put it on the left, okay? We expedite a little bit. And they should be equal to, for the left hand side, we put it on the right, so it will be E sub m times the quantity S sine of angle P plus omega cosine of angle P all over S square plus omega square. I will check my camera. Okay, it's still fine. So if we try to compute for capital letter I as a function of S, okay, we will take the right hand side, then divide by this, okay? But the simplification of this will be an LCS square plus RCS plus 1 all over CS, right? So this will go up, because if we change the operation from division to multiplication, this should go up. Okay, so I capital letter S as a function of S should be E sub m times this quantity here all over this, but the simplification of this is actually CS all over LCS square plus RCS plus 1. Because R times CS is actually RCS, right? And LS times CS is actually L times C. S times S will be S squared. So this is to be multiplied by S squared. Okay? This is plus 1. This is actually all over CS. But we change the operation from division to multiplication, so this should go up. So this is now CS. Oh, What will come out now? Capital letter I as a function of S will be equal to, I will combine E sub M and CS, I will put it here, times the quantity S sine of angle P plus omega cosine of angle P all over under one denominator. The simplification or the simplified form of S square plus omega square is actually S plus j omega times the quantity S minus j omega. And for this thing here, it's a quadratic equation. The unknown is actually S. Because the inductance is constant, the capacitance is constant, so the product LC will still be constant, and that is actually A. Right? R is constant, capacitance is constant, the product of two constant will still be constant, so the product RC is actually B. Okay? Plus C. The value of C is actually the pure constant term on the quadratic equation. And I will put capital, this is small c, the capacitance, and capital letter C will be the value of the C on the quadratic equation, that is capital letter C will be equal to 1. So actually, this quadratic equation, okay, what they call this, the simplified form will be S times the quantity S minus 1 times the quantity S minus S2, meaning S1 will be the first root of S, and S2 will be the second root of S. So meaning, this quadratic equation has two roots, so I just place it as simply S minus S1 times the quantity S minus S2. Okay? And if you try to notice this one here, linear equation, they are just imaginary. Linear factors rather. Linear factor, they are what they call this imaginary part, and S minus S1 will be a pure linear factor. This is pure linear factor. So actually the denominator contains 4 linear factors. And if we try to simplify this one, the one with the J is actually the solution of the particular solution, I sub P. This portion here. And this portion, here, sorry for that one. The quantity S minus S1 times the quantity S minus S2 is actually I sub C, meaning the complementary solution. So actually the solution got two components. The capital letter I as a function of S with the subscript C is actually this equation here. We are considering these two factors here, S minus S1, S minus S2. And for the particular solution, okay, it will be AMCS as this, considering the two imaginary factors, S plus j omega, S minus j omega. It is this. Okay? Let's do first the complementary solution. If we try to factor out or to solve for the value of S here, okay, I will bring out, it will be LCS squared plus RCS plus 1 equal to 0. It is really a quadratic equation. So meaning, to solve for S1 and S2, we must have to compute for the value of S. And unluckily, we could not solve this by using the so-called factoring by inspection. So we must have to use the so-called quadratic formula, in which the value of A will be LC, the coefficient of S, and the value of B will be RC, the coefficient of S, and the pure constant is actually 1. So by using this equation here, substituting the value LC, RC in 1, okay, I will not venture into the so-called simplification. I will just give you the final value of S1 and S2. The value of S1 is actually this. Okay? And the value of S2 is actually this one here. Okay, if you try to simplify this one and substitute the value LC, RC in 1 back here, then try to simplify. Okay? Actually, S1 is by using the plus sign, and S2 is actually by using the negative sign. So these are actually the roots. And for the meantime, we do not know the exact value of S1 and S2, so we will just place it in general. The simplified equivalent of this will be the quantity S minus S1 times the quantity S minus S2. So for the complementary solution, if we try to consider this function here, plus this, and this portion, that refers to the complementary solution. It is this. Okay? And the equivalent of this will be, since there are two linear factors over here, the equivalent will be EMCS times this, times the two partial fractions A over S minus S1 plus B over S minus S2. So meaning, to compute for the value of I sub C, we must have to compute for the value of A and B, then try to do some algebraic manipulations to arrive at the so-called complementary solution. Okay, I will try to check my camera. Okay? So for the complementary solution, we must have to compute for A and B. For the meantime, we will not compute for the value of A and B. We will just discuss the three possible cases that will come out. Okay? For case number 1, if after the computation of S1 and S2, S1 is not equal to S2 and they are both real, okay, what will come out will be S1 will be equal to alpha plus beta and S2 will be equal to alpha minus beta. Alpha is real, beta is real, so the sum of two real numbers will still be a real number and the difference of two real numbers will still be a real number. That's why under case number 1, S1 is not equal to S2 and they are real. The solution, if luckily it falls under case number 1, this should be the solution of the complementary solution. Okay? That's the complementary solution if it falls under case number 1. For case number 2, if luckily S1 is equal to S2 and they are both real, if they are equal, whether we like it or not, beta will be 0. Because for these two rows here, S1 and S2, for them to be equal, they should be 0 and they should be 0 for them to be equal. So I place it here, S1 is equal to S2 and it is equal to alpha. Okay? And beta, whether we like it or not, should be equal to 0 for them to be equal. Okay? And the complementary solution, if it falls under case number 2, this should be the complementary solution. Okay? For case number 3, if S1 and S2 are complex conjugates, meaning they are complex numbers, they got the real part and the imaginary part, what will come out will be S1 will be equal to alpha plus j beta, real part, imaginary part. S2 will be alpha minus j beta. S1 is by using the positive sign, and S2 will be by using the negative sign. They are complex conjugates. They are of same value, but the sign of the imaginary part is the reverse of the first one. For case number 3, the complementary solution will be this one. Okay? So actually, in the total current, there are 3 cases for the possible solution of the complementary solution. Case number 1, case number 2, and case number 3. For the meantime, I will not give you the value of A and B, but as a rule under Laplace transform, to bring out these 3 solutions here, we must have to compute for A and B. In whichever case that will come out, just use it. If it falls under case number 1, the solution should be under case number 1. If it falls under case number 2, the solution should be under case number 2. If it falls under case number 3, the solution should be under case number 3. Okay, let's proceed with the so-called particular solution. Okay, for the particular solution, it is just E sub MCS times this. Then we will consider the denominator to be S plus J omega, S minus J omega, it is this. Right? And if we try to compute for the particular solution, it will be EMCS times this quantity here, times an unknown number D all over S plus J omega, the pulse linear factor, under the particular solution, plus E all over S minus J omega. So to compute for the particular solution, compute for the value of D and E. Okay, we will not venture into that. It was a long process. It is just an algebraic manipulation. So if you try to do it, I will not show it here. We will lack space. Okay. But I will give you a shortcut on how to compute for the value of the particular solution. Under AC circuitry, the particular solution is actually E sub m over z. We will just divide the applied voltage by the impedance, but we must have to use the so-called polar division. We must have to place the proper angle. So the particular solution is actually E sub m over z. And if we try to perform the polar division over here, whatever the angle on the numerator, okay, you subtract that with the value of the angle on the denominator. So this will rise up. So it will become either, if this is plus, if it goes up, it will now be minus, right? And if this is minus, if it will go up, it will now be plus. So no matter what, the sign of this will either be a plus or a minus. So for the particular solution, okay, it will be E sub m over z, absolute value. And the total angle will be omega t plus angle p plus or minus theta. Okay, this plus here, if the angle is plus theta, we could say that the value of the capacitance is larger than the inductive reactance, so it will be leading current. If this is plus, it should be leading current. And if this is minus, it will be inductive, it will be lagging current, meaning the loads are motor loads, something like that. So actually, if we now try to bring out the total current as a function of time, it will be the complementary plus the particular. And the value of the so-called particular is this one. Or you could bring out this one by taking the value of D and A by using algebraic manipulation, then take the inverse Laplace. Whether you like it or not, what will come out will be E sub m over z. The angle will be omega t plus angle p plus or minus angle theta. So for the final answer on the particular solution, it will be E sub m over z sine of the quantity omega t plus angle p. This is plus or minus theta. So if it is plus, it will be capacitive. If it is minus, it will be inductive. So this is the total current as a function of time for an RLC-AC by using Laplace transform. I then show you the computation of D and E and also the value of, where's the other one? A and B. Okay. I just summarize it. It is by using algebraic manipulation, what should come out will be the three cases. Okay, for the particular, it will just be simply only one. Okay, but you must have to compute also for the value of D and E, then take the inverse Laplace to bring out this equation supposed to be. This should be the same. Okay, okay, that's it, guys. That is the simplified solution of an RLC-AC circuit by using Laplace transform. I didn't show you all the algebraic manipulation. I just discussed it how we could do it. And supposedly this is now the total current as a function of time for an RLC-AC circuit. Three possible cases for the complementary. And the particular, it's just a simple thing. It will be E sub m over this sine of the quantity omega t plus angle p plus or minus theta. That's it. So for those of you who are taking what they call this advanced mathematics, this is the solution of an RLC-AC circuit by using Laplace transform. It is by using algebraic manipulation, then try to take the inverse Laplace so you could bring out the two solutions, complementary in particular. And unluckily, this is the worst case scenario for a circuit analysis because the complementary solution, we could bring out three possible cases for the complementary. And for the particular, it is just a simple thing. That's it. If you want to subscribe to my channel is at youtube.com/ProfDavidJDelosReyes. Okay, and if you want to share it, please click share. Good evening from Los Angeles.